Okay, this lesson is going to closely follow our last lesson about normal distributions. Uh, we're going to be talking about z-scores. And let's first off start off by defining what we mean by a z-score. A z-score is a value that shows how many standard deviations a data value is from the mean. So again, a z-value is simply telling us how far are we from the mean? Are we one standard deviation? Are we two? Are we -1, -2? So from what I just said, we can have positive and negative. If the z-score is positive, the data value is above the mean. If it's negative, then it's below the mean to the left. When z is equal to 0, if you have a z-value of 0, then the data value is equal to the mean, and that's all a z-score is. We do have a formula for a z-score, and excuse my variables here. A z-score is simply your data value x minus your mean. Remember that's the Roman Greek letter mu divided by the standard deviation, which is denoted with sigma. So your z-score, in order to find it, you're simply going to take your value, subtract your mean, and divide by the standard deviation. This process is actually called normalizing. We're turning it into what we're about to see is a standard normal curve. So let's try it in our examples here. Example number 1 says a radar detector records the speeds of a group of cars that pass. If the mean is 46 and the standard deviation is 2.8, find the z-score. And again, what we're looking for is how far are we from the mean? How many standard deviations? So our z-score, again, we're going to take our value, we're going to subtract our mean, and simply divide by our standard deviation. So 52 minus 46 divided by 2.8, and we get a z-score of 2.14. Now, again, we need to understand what that actually means. 2.8, one standard deviation from the mean is 2.8 away. So what we are actually a little over 2 standard deviations from the mean. And since it's a positive, again, we remember our bell curve from our last section. So if our mean is here, we remember we had the 1 standard deviation here. We remember our percentages, and 2 standard deviations here, and 3 standard deviations here. So we would be somewhere about right there, 2.14 standard deviations above the mean. Again, the next one, 42. So we do our value minus our mean, and we divide by 2.8. And that's going to tell us how many deviations, standard deviations we are from the mean. And we get negative 1.43, which again, since it's negative, tells us we're a little over 1 deviation below the mean. And the last one, we have a value of 47, which we know our mean's 46, so we know that we're going to have a positive deviation here. So it'd be 47 minus 46, and simply divide it by 2.8, and that tells us that we are 0.36, a little less than half of a standard deviation away from our mean, which means we're really close, and that makes sense because we're only a value of 1 away, and it's 1 in the positive direction. And we're not quite, just something to think about, we're not quite a whole standard deviation away, because a whole deviation would be 2.8, but we're only 1 away and not 2.8 away. Number 2 says the mean of the total miles ran by each member of a track team was 4. So I'm going to underline that. That's important information. The standard deviation is 1.2. If Clay's z-score was 2.5, how many miles did he run? So we can actually start with the actual formula that we use to calculate z-scores. Again, a z-score is your actual value, which is what we're looking for here, minus our mean, divided by the standard deviation, and plug in the values that you actually have. It says the mean was 4, standard deviation is 1.2, and the z-score is 2.5. So we have the z. We are looking for the x value. We have the mean, which was 4, and we have the standard deviation, which is 1.2, and that gives you a very basic equation to solve. Since it's divided by 1.2, we're going to move that over by multiplying. And we actually get 3 when we do that, so we now have 3 equals x minus 4. Move the minus 4 over, and we get our value is 7. So the actual amount run was 7. So, and we see that if the mean was 4, he is above the mean there. He's actually, if you try to calculate it again, he's going to be 1.2, or excuse me, 2.5's his z-score. So 2.5 deviations, standard deviations above the mean. Number 3, a set of test papers is normally distributed with a standard deviation of 5. Riley's score was an 83 and a z-score is negative 0.4. What is the mean? So again, all we do is start with our formula. Our z-score is equal to our value minus our mean divided by our standard deviation. If our z-score is negative 0.4, we have a, let's see, do we have the actual value? I believe we should. Riley scored an 83. We are looking for the mean, I believe, and the standard deviation is 5. So he's going to be a little bit less than half of a standard deviation below the mean. So let's try to solve this. Again, step number 1, since it's divided by 5, let's move that over by multiplying. We now have negative 2 equals 83 minus mu. We can solve this a couple of different ways. The way I prefer, since it's a negative mu, let's move it to the left side, make it a positive mu. Move our minus 2 to the right, making it a positive 2. So that tells us that our average is going to be an 85. So you see with a score of 83, he was slightly below the average. Number 4, the highest of a group of trees is normally distributed with a mean of 14.3, a z-score of 20, or if the z-score for a 20-foot tall tree is 1.9, what is the standard deviation? So again, our z-score is equal to the value minus the average divided by the standard deviation, which is what we're looking for. So this one's going to be a little bit trickier. Our z-score, the z-score is 1.9. The value, let's see, the highest of a group of trees is normally distributed with a mean of 14.3. If the z-score for a 20-foot tall tree, so our actual height is 20, it says the average is 14.3, and we are looking for sigma here. So maybe it won't be as hard as we thought. So we've got now 1.9. We can subtract these two values. So let's go ahead and subtract that and get 5.7 divided by sigma there. Now, there's a couple of different ways to look at this. What I like to do is to think of it as proportion. That's one way. And to solve proportions, if you don't remember, you multiply 1 times 5.7 and you'll divide by 1.9. Another way is to go back and think of what we did when we dealt with trigonometry, sine, cosine, and tangent, because it reminds me of that problem. When the variable was on the bottom, there was a trick that you could do. You could actually just switch these two values, and you'll get that your sigma, or your standard deviation, is going to be 5.7 divided by 1.9, which is 3. Okay, finally, we're going to define what we mean by a standard normal distribution. And not just a normal, but a standard, the standard one. And here's what you got with standard: a normal distribution in which the mean is 0 and the standard deviation is 1. This distribution is standardized by the z-score. So what do we mean by standardized by the z-score? You can see here this is a standard normal distribution. And you can see that if 0 were our mean, a value of 1 would be the same thing as a z-score of 1, because our standard deviation is 1. A standard deviation of 2 would be the same thing as a z-score of 2, and the same thing in the negative direction. Now, I did want to go back and talk about this formula, the z-score formula. And I want you to think about how it works. Notice what I've done. I drew a normal distribution here that actually has a mean of 250 and has a standard deviation of 10. You see that I've got the 260 above it, the 240 below it. So there shows my standard deviation. So what does this formula actually do? When you take a value like 250, let's say that you're at 250 and you subtract off the mean, that 250 would go to 0. 260 would go to 10, 240 would go to negative 10. So when you subtract the standard deviation, what you've actually done is, or excuse me, when you subtract the mean, what you've actually done is carried this curve from 250 to 0. But however, the only problem is now these values are at 10 and negative 10 and 20 and negative 20. So what happens when I divide now by the standard deviation? This value of 10 now goes to 1. This value of negative 10 would go to negative 1. What would be at 270, which would be our 2 standard deviations away from our mean, would be now 20 divided by 10, which would be 2. So that's the reason that this formula, what I was saying, this formula, sometimes we say that we are normalizing, that we're making it, standardizing, not normalizing. We're standardizing our curve when we're carrying it from this to a standard normal by using this formula. Okay, the next part says calculator directions, but I actually want to do this a little bit different. We want to show you how to do this with what we call a z-score table. It says the golf scores in a tournament is normally distributed with a mean of 76 and a standard deviation of 2.6. Find each probability. Now I want to point out that it says the probability that z is less than 2.1, and here it says probability of x is less than 74. Z is a z-score. So that means that you're 2.1 deviations away from the mean. Let me kind of sketch this out for you. Okay, here's my normal curve, normal distribution curve, and I just wanted to draw this to remind you and show you what actually you're doing here. Before, if our standard deviation was positive 1, then between 1 and 0, we had 34% of our probability. Between negative 1 and positive 1, that was 1 standard deviation. We had 34.1 and 34.1, 68.2% between those two. So that's all we're doing here is we're saying, what's the probability? Let me draw my actual numbers here. -2, -3, -4. So when you're saying the probability that you have a z-score of 2.1, that you're less than 2.1, well, 2.1, let me change colors here. 2.1 is slightly to the right of 2. So we're simply saying the probability of being less than 2.1 would be this and this and this and this and this and this and some more added together. So we're going to be somewhere around, let's see, this is to the right is only 2.2 and 0.1. That's 2.3, but it's going to be a little bit less than that to the right. So about maybe 2.1. So we're going to be somewhere around 98% of our values is going to be less than 2.1. So let's flip over here and let me show you how to actually use one of these tables. So we'll show you a picture here if they've got it. What these z-score tables are, I thought there was a picture involved. Let me zoom out and see. There might not be. Maybe not. This is simply telling us the percent, or it's given us as a decimal, the percent that is lower than this z-score. I want to point out, notice 0.0 right here. 0.0, just look at the first column to begin with. 0.0, 50% of my probability is lower than 0.0 because 0 is right in the middle. Go down to a standard deviation of 1 right here. 84% of my values are below 1. And if we go back that's backed up by this. Here's one standard deviation away. All of this added together would be 50% plus another 34, which is that 84.1%. So all we have to do to find the probability that we're 2.1 away, well, what we're going to do is we're going to scroll down to 2.1, and we're going to look right here, and we see that we are 0.98214 right there. So 0.98214, let me close that. So 0.98214, or that would be a 98.2 if we want to round it off, percent probability that we're below 2.1. So let's try one more with just a z-score before we change it over. The probability that our z-score is greater than negative 1.5. So negative 1.5, we have our 0, our mean, right in the middle. Negative 1 would be here, and negative 2 would be here. So we're somewhere right in the middle. We want to know the probability that we are greater than negative 1.5. So here's what we can do. We've got to remember that this thing is symmetrical. So what we can do, the probability that we are, well, hang on a second, okay, we're looking for the probability that z is greater than negative 1.5. And let me draw this scenario for you. And I want to show you how I actually like to do these. I use the symmetry a ton. So what I'm actually looking for is the probability that we're greater than 1.5. So we're looking for all this area over here. So I do want to tell you that it obviously is going to be greater than 50% because here's our mean, and this is half of our area. So we're a little bit bigger than 50%. We've got to add this part of the area on. So let's think about using a positive value there. So probability that z is greater than negative 1.5. Let me draw another drawing here. And what I've done here is I've drawn a deviation, normal distribution curve here with a positive 1.5. And I want to point out that everything greater than negative 1.5 would actually match up and be identical to everything smaller than positive 1.5. So then it's really easy to use our z table here. All we've got to do is this is the percentages below these amounts. So we go down to 1.5. We find out that 93.319, if we change that to a percent, so we'll round that off to about 93.3% of our value is below positive 1.5, and that would match up with how much is actually above negative 1.5. Now let's go back to number 6 and show you how that actually corresponds with what if they give you an actual value. Just a quick reminder that in order to find a z-score given an actual value is you take that value, you move it left, whatever the mean is. So notice we're going to have a negative z-score here, and then we're going to divide by the standard deviation. So on this problem, number 6, we get a z-score of negative 0.77. So what we're looking for is how much, here's our mean. So negative 0.77 would be a little bit left of the mean, would be right there, not quite one standard deviation away. So we're wanting to know how much of our probability is lower than that z-score. Now you can use the trick that I showed you on number 7, or I'll go ahead and break the good news to you that there's actually tables for negative z-scores as well. So we'll just use that on this. So here's my negative z-scores. And again, remember that negative z-scores simply mean it's to the left of the mean. Now, I'm about to show you what all these other numbers actually mean on your table. These other numbers are hundredths place. So you have, if the hundredths place is a 0, as we see right here, like let's do this negative 3.9 here. This would be negative 3.90, negative 3.91, negative 3.92, negative 3.93, and so on and so forth. So to find negative 0.77, we first have to go down to negative 0.7, which is right here. and then go over to our seventh, let's say that'd be 0, 1, 2, 3, 4, 5, 6, 7. So this would be negative 0.77. Move our decimal over 2 times, and that'd be 22.065, which we'll call 22.1 as we round it. About 22.1% of our probability is below 74 or has a z-score of negative 0.77. And again, what we actually found, sometimes it's good to revisit the problem, is the golf scores are normally distributed. The mean is 76. So how many of these golfers, if the standard deviation is 2.6, how many of these golfers are shooting below a 74? And that would only be about 22.1% of those golfers would be shooting that low. Now, 8.1. If we've got 76 as our mean, how many are shooting above an 81? That's a pretty high score when the standard deviation is only 2.6. That's nearly two standard deviations away. So I would say that that's going to be a fairly low number. So again, we want to change that to a z-score. To change it to a z-score, we're going to take our 81, we're going to subtract our average and divide by our standard deviation. And we find out on this one that our z-score is a 1.92, which again, notice that our z-score there is nearly two standard deviations away. So now what we're actually just doing, and you can rewrite it if you'd like, to find the probability that your z-score is greater than a 1.92, or how many golfers are 1.92 standard deviations away in the positive direction from your mean. So we go back to our table, and that's a positive value. Now we've got to do some work on this one. You got to be careful. So here's 1.9, here's 1.90, 1.91, 1.92. So that's 97. We'll call it 97.3 when we round it. Let me write that down though. Because that, when you're looking at those tables, your z-score table gives you the values below that z-score. We want to know how many, what percentage of our golfers are above. So we've got to take that 97.3, subtract it off, because underneath the curve, we have 100% of our, under the curve, 100% of our probability is denoted there, is symbolic with that curve. So the other portion would be 100 minus that 97.3, which would only be 2.7% of our golfers are shooting above an 81. Okay, now we'll work some sandwich problems here, to where we've got what's the probability that our z-score is sandwiched between negative 0.2 and 1.8. And I've drawn a picture of this. Here's our standard normal curve, and we're wanting to know that the probability that we're between 0.2, which is right here, and 1.8, which is nearly two standard deviations away. So here's what we're going to have to do here. See if you follow this. We're going to find from our table the probability that we're below 1.8, which is actually going to give us this whole probability from 1.8. Just a quick reminder that your table gives you the total probability below that z-score. But we don't want all of this. We only want it from here over to here. So we're going to find the whole probability. Then we're going to find on our table what's the probability that we're below 0.2, which would be this value. And in order to find this, we're simply going to take the whole and subtract off this part. And that's going to give us the probability that's right here in the middle. So first off, the probability that your z-score is, let's start with less than 1.8. So we go to our table. 1.8 would be right here. It would be a 96.4% probability. That's a 4. And then we're going to do the probability that our z value is less than negative 0.2. So we go back and we need our negative z-score table. Negative 0.2 right there is 42.1% when we round it. So that tells us that 96.4% is below 1.8. 42.1% is below negative 0.2. So how much is between the two values would simply be the difference between those two, which would be a total of about 54.3% of our values would be between negative 0.2 and 1.8 on our z-scores. Okay, our last one. And again, we just have to standardize this first. So we're going to take both of our values, and let me write down the mean and the standard deviation again. So now let's change that to, instead of our actual values, our actual golf scores, let's change that to a z-score instead. And just quick reminder of all that you're doing to do that is you're going to take your value, subtract your mean, and divide by your standard deviation. And I'm going to do that for both of these values. And I get simply 0.38 and 2.69. So what you're doing here is the probability that your z value is between those two. So 0.38, if this is my mean, 0.38 would be somewhere right in here, and 2.69 would be somewhere over here. So that's what we're going to do, is find that area right there. We're going to follow the same process. We're going to use 2.69 and find how much of the area is below 2.69. Then we're going to find out how much of the area is missing over here down below 0.38. And to find this shaded in region, we're simply going to subtract the two. So let's find each of those areas to begin with. And a lot of people are thrown off by why does it say it's greater than 0.38 here, but we're using this less than 0.38 here? Well, the actual area we're looking for is what's greater than 0.38, but we're going to have to use all this area that's less than 0.38 to deduct from this total area so that we can find that area that we're looking for. So let's look at our z-score chart. So the probability that z is less than 2.69, let's go to our positive. So 2.6 is here. So 2.6, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Be right here. That'd be 99.6%. So most of our area is below that, and we know that because that's nearly 3 standard deviations away. So most of our area is going to be below 2.69. Now, how much of our area is below 0.38? So 0.38, we go to 0.3, and 0.38 would be located right here. So 64.8% is below that. So let's go ahead and write that down, 64.8%. Now, to find the area that is shaded, that would be the total area up to that point, which is 99.6. But we're going to take away this portion of it, which was the 64.8, and that's going to leave us with 34.8% of your area is between those two values. And again, let's get back to what are we actually finding there? What we did with that problem is we found out the probability that we have a golf score between 77 and 83 if 76 is the average. So all of those are above average with a standard deviation of 2.6. So that tells us that our scores are pretty tightly packed because our standard deviation is pretty close to 1 there. So we've got some pretty tight scores, but the probability that we're going to score between a 77 and 83, we have nearly a 35% chance, which is a pretty good chance of scoring between that range when we have this set of data.